At first glance, the expressions with their derivatives shown here seem ridiculously erroneous. But bear with me here so I can show you how they may not be as far off as you'd think. It should be fairly obvious that the derivative of the area of a circle is the circumference of that circle, and there are plenty of YouTube videos out there about that topic. The better videos show this by going into the definition of the derivative and showing how the derivative definition applied to the function pi r squared ends up reducing to 2 pi r when dr goes to 0. Simple enough if you've thoroughly studied the definition of the derivative for more than just a day or two. Now this works well for the formula of a circle, but why not a square? Or a rectangle? Or a triangle? Intuitively, one would say it probably doesn't work because a circle has a constant radius and the other shapes do not. But what if we want to play around with shapes and derivatives and see what happens? It's the kind of mathematically crazy thing I would normally do. Why? Because I'm still crazy after all these years. Let's take a square with side s. Its area is s squared, and its circumference, or perimeter, is 4s. Now, 4s is clearly not the derivative of s squared if we use our normal power rule of differentiation. 2s would be. But just because something does not obey the power rule of differentiation, does that mean it cannot be a derivative? Can it still fit the formal definition of a derivative? Go back to the definition of the derivative and the drawing of a circle, and notice that dr encircles the entire shape. What would happen if we did that with a square? If we surround the shape with a distance of ds from each side, we notice the area of s plus ds involves 2 ds's in the base and 2 as well in the height. So it's really s plus 2 ds we're going to use for the side of the square. So it's a bit different from the circle. Let's try plugging the formula for the area of this thing into the derivative and see what happens. We start with our s plus 2 ds squared minus s squared over ds. Write out the expanded power with the FOIL method. Cancel out the s squareds. Divide by the ds. Finally, take the limit as ds goes to 0 and we get 4s. And guess what? That is the formula for the perimeter of our square. Seems like magic. Fairly simple magic, but still magic. You'd use a similar process for rectangles. It's just not that much more exciting than the square. But you'd have to do it with a rectangle with a specialized proportion, and not a general one, since you use just one variable in the derivative. Might as well proceed and try a specialized proportion triangle. We'll try a simple 45, 45, 90 triangle because that's the easiest one I know. Call one of the legs S. This triangle has sides S, S, and S square root of 2. Area would be 1/2 S squared, and perimeter would be 2 plus square root of 2 times S. Now surround it by another triangle with a distance of ds from each side. It's easy to compute the addition to the sides of the triangle at the 90-degree angle corner, but the 45-degree angle corners are not quite as straightforward. We have to use a bit of what we know from geometry and really zoom in on that corner to figure out what to do. connecting the corner points of the inside and outside triangles, we deduce that they form congruent triangles by the hypotenuse leg theorem. The triangles share the same hypotenuse and have ds as a congruent leg. From there, we can figure the angles of the congruent triangles are 90, 67.5, 22.5, if you follow the logic of the drawings. Once you know the angles, you can find out the length of the addition to the corner, labeled here as a question mark. Turns out this length is 2 plus root 2 over root 2 times ds. Man, that was a bit involved. But now the rest of everything is straightforward if we manage to stay careful with the upcoming algebra. We know both legs of the outer triangle now that we've added the excess from each corner. So now we know the area of the outer triangle, and we can plug it into the definition of the derivative and see what happens. Will we get the perimeter as we did with the square? At this point, it would be nice to have a series of those movable whiteboards to write everything on. I know it looks a bit cluttered here, but at the top left, we plugged the area into the definition of the derivative, and that's it. Then we condense the two ds's in the expression that gets squared. Then we break up the numerator of the stuff over the radical, because the root 2 over root 2 nicely cancels out to 1. Then we add up that 1 to the other 1 inside of the squared expression, and that's the most we can do on this screen. Now we carry over that result to the top of the next screen, and we finally see that we can just divide 2 by root 2 to get plain old root 2, and we're finally ready to use the FOIL method to expand the expression in the square. I suppose we could have tried sooner, but I figured it would have been even worse than what I did here. Some of the stuff was too messy to write, and it's in front of a ds squared, which when divided by ds will still have a ds that will go to 0. So I just labeled it as junk that will cancel, because it will. Now in the next screen, I've done two things. I've distributed the 1/2 through the expression, and I've canceled out the ds at the bottom. Once that thing is canceled out and there are no ds's at the bottom of fractions, things look a bit promising. We take the ds to 0, and indeed the junk cancels, and we're left with two things that will subtract each other out, and a 1/2 and a 2 that will cancel out as well. We're left with 2 plus root 2 times s, and indeed that is the perimeter of the triangle. Coincidence? Perhaps. Algebraic error? Maybe. Or maybe we're on to something here. I think that not only with circles, but with pretty much any closed shape, there's some kind of quote-unquote derivative of the area that equals a circumference, if we just choose carefully what to plug in for the f of x plus dx portion. The idea behind these is that the circumference is some kind of measure of the change in area of the shape. Perhaps a real mathematician can show that better than I can, if that happens to be the case. I'm just a fake one, an amateur at best, but it doesn't mean I'm automatically wrong. I was hoping to do the same strategy with an ellipse with a semi-minor axis half as big as its semi-major axis r, but an ellipse doesn't have sides, so I didn't really know how to do a distance of dr away from each side. I naively just tried doing the dr at the end of the semi-major and semi-minor axis, hoping that would get me the circumferences I was seeking. But it seemed too far off when I used an online circumference calculator to be correct. I have no idea what other option I can use. Now I've run out of ideas again, so I guess I'll go do something else. If anybody watched this, thanks for watching and have a nice day.